Hello my little making chums, I'm Pommy Tim coming to you from sunny South Australia. Now today I want to walk you through a really super simple project, but it involves a couple of techniques that if you can master them, it's going to dramatically improve your making and particularly your woodworking game. Did you ever sit in maths class when you're at school doing algebra and thinking to yourself, is anyone going to tell this idiot teacher that none of this nonsense is ever going to be used in the real world? Well, that time is now. I've got a sink sitting in my backyard that I've been meaning to repurpose for some time. Now I want to build a support for it because I want it to sit at waist height, but I don't want to build anything with legs because I want to be able to sweep underneath it without any difficulty. So I'm going to build a base with angle brackets to support the weight. On a build this simple, you could cheat by cutting your brackets with 45-degree cuts and basically guesstimating the length of cut. But what if you want to cut a more severe angle and be more accurate in your calculations for your length of cut? How do you go about that? There are two main equations relating to triangles that we'll be using in this video. Now, don't panic. You don't have to memorize any of this. There will in fact be a cheat sheet at the end of this video that you can copy and keep for your own reference. All you need to know is how it works and how you can apply it to your own projects. Now as a carpenter, I have used these methods regularly, especially when pitching hand-cut roofs. But these methods can be applied to a myriad of smaller projects. For example, if you were building a table with splayed legs, or if you were building a chair and you wanted the back to be more comfortable than something that merely stood vertically. I know the dimensions of the base of the sink, which is 450 by 450 millimeters, and I'll be using 70 by 35 millimeter structural pine, illustrated by the elevation shown. And I want to use a 35-degree angle at the bottom of my bracing to make the bracing pieces slightly more vertical and give a greater level of support. Very simple rule number one. All angles of a triangle equal 180 degrees. I know that one angle will be 90 degrees as it comes horizontally off the wall, and as stated earlier, I want the bottom angle of my bracing to be 35 degrees. Simple calculation, 180 minus 90 minus 35 leaves us with a final angle of 55 degrees. So we know our angles, but how do we work out our lengths of cut? Well, this involves a simple-ish equation. We can see that the bracing I want to build is made of a triangle, to which I shall assign the letters capital A, B and C for the three angles, and the letters small a, B and C for the lengths of each side. Each capital letter will always sit directly opposite its corresponding small letter. This part of the calculation relates to the rule of sine. If you've ever looked at a scientific calculator, you'll have seen a button labelled sine, spelled S-I-N. Now this part you don't have to worry about unless I've marked it in red, but it's handy to know how the calculations work. So the rule of sine states that the length of side A divided by the sine of angle A will always equal the length of side B divided by the sine of B and the length of side C divided by the sine of angle C. We know the length of side A, which is 415 millimeters, and we know the angles of A, B and C, which are 35, 55 and 90 degrees respectively. If B over sine B is equal to A over sine A, then this can be rewritten as B equals side A times the sine of angle B divided by the sine of angle A. You don't need to understand how this was rewritten, you just need to accept that it works, so don't panic. We know that side A is 415 millimeters. If you go to the calculator on your computer, select scientific mode and press 55, which is the degree of angle B, followed by the sine button, you'll get a calculation of 0.819. Likewise, press 35, followed by the sine button, and you'll get a figure of 0.574. All we have to do then is multiply 415 by 0.819 and divide the answer by 0.574, which will give us the length of side B as 592 millimeters, rounded to the nearest whole millimeter. So we now know the lengths of two of our pieces of timber, but the tricky length to get right, and I've seen seasoned professionals struggle with this, is the length of the side of timber, length C. Again, we know that by the rule of sine, C over sine C will equal A over sine A, which can be rewritten as, and again, this is the important part, length C will equal length A multiplied by the sine of angle C divided by the sine of angle A. Using the scientific calculator again, 90, which is the angle of C, followed by the sine button, will give us a value of 1. From our previous calculation, we know that the sine of 35 degrees is 0.574. So to calculate the length of C, we multiply 415 by 1, which obviously gives you 415, and divide that by 0.574, which equals 723 millimetres, again rounded to the nearest whole millimetre. Transfer that information back to our plan and we can see that for each brace we need a length cut at 450 millimetres, which is the 415 of our triangle plus the 35 millimetre width of our timber. We need a length cut at 592 millimetres and a piece cut on the long side at 723 millimetres with one end cut at 35 degrees and the other at 55 degrees. So all that information took very little time to calculate, and as they say, the maths doesn't lie. No need for guesswork, I know exactly what I need to cut. So this is the cheat sheet showing all the information you'll need to ensure that you get every angle cut right every time. I've been Pommy Tim, my sincere thanks for watching, hit that subscribe button and have a great day making something great.